Alright, let's talk about work and how it applies to rotational kinetic energy. Remember we said kinetic energy, if something is rotating, is 1/2 I omega squared. If we'll see in the next chapter, it could be translating and rotating, so maybe it's spinning with some omega while it's moving with some velocity v. Then the kinetic energy will be 1/2 mv squared plus 1/2 I omega squared. Now we're going to make some analogs. So we said before that the change in kinetic energy was equal to work, the amount of work done. And we could say, okay, then the work was equal to 1/2 mv final squared minus 1/2 mv initial squared, right? We also said that we could calculate this by taking an integral definition of f dx from x1 to x2. And for now, let's just talk about one dimension. We also had one more definition. It said that the power is equal to either the time derivative of the work or the force times the speed, once again in one dimension. Well, we can also calculate the change in kinetic energy, or the work, as 1/2 I omega final squared minus 1/2 I omega initial squared. So if you know something's angular velocity at 2 points in time, then you can figure out how much work was done to get that thing to rotate to that omega final from some omega initial. You can also figure out the work done using an integral definition. We could say if we have a torque acting through some differential theta, right? So a radius arm here, a torque, it acts through some distance theta, so from some theta initial to some theta final. We can also calculate the work. And if the force or the torque is constant, we can reduce this one to the work being equal to the torque times the angular displacement, and this has to be in radians. All this stuff that has to do with rotations has to be in radians. So we could say the work is equal to whatever that torque is minus, or theta final minus theta initial. So you just need to know two angular displacements and what was the torque what was the torque that was doing that work. So that gets us these definitions right here. And remember, if this was constant, also this definition reduced to f delta x. So we have a variable. This could be a torque as a function of theta, or we have if we have a constant torque applied the whole time. Okay, one more. We can take this power definition, and the work part doesn't change. Power is still equal to d omega, or d, the change in work with respect to time, dw dt. But instead of f times v, it's going to be torque times the angular velocity. So it just gives us three new equations for rotations that we can use that have to do with work, rotational kinetic energy, and instead of force, we're dealing with torque. Just know that if something's rotating, we're typically going to deal with the moment of inertia, not just the mass, but how it's distributed. If something's rotating, we're typically concerned with the torque, not just the force. We need to know what's this distance that the torque is acting at, or the force is acting at, causing torque. And everything should be in radians. Radians per second, radians per second squared. Alright, let's wrap up this one.